So now we're ready to pick a real protein structure from the protein data bank, and I've done that for you. Here is one. It's the beginning of a file. Simple old style files from the 1970s. Each line in this file corresponds to an atom in the protein. Number of atoms, the name of the atoms, nitrogen, Ca stands for C alpha. I can't use Greek letters here. CO are also backbone atoms. Cb is C beta, Cg is C gamma. OD1 and 2 is oxygen delta 1 and 2. Again, the Greek letters. And that's an asparagine side chain, ASP. A means that this is the first chain in the entire protein. If there is ever a break and move over to another polypeptide sequence, that would be B. This is the number of the residue. The X, the Y, and the Z coordinate measured in angstroms of those residues. People tend to use angstroms in structural biology. This column we're not going to care about, and that column is actually has to do with those temperature factors, but in the interest of time, I won't bother you with that. Based on this, we could actually let a computer take this and translate this to parameters, add the force field, add all the bonds, torsions, partial charges, and everything from the recipes in that force field, and set up a simulation based on this. But before we do that, do you see something missing here? Or rather, is there something you don't see? There are no hydrogens, right? That's very common. That hydrogens are frequently not that visible, in particular not in X-ray structures, because it's the electrons that are responsible for the interaction with the electromagnetic field. And the electrons are going to be shared with the bond to the closed heavy atom, right? So the hydrogen per se is almost only a proton. There are a few high-resolution structures today where you see them. You will see them in NMR structures too. But it's going to be very common in the protein data bank to have structures without hydrogens. That's actually one of our least issues, because the programs we all have, if I know what the heavy atoms are, I know what the amino acids are, I can reconstruct and calculate what the positions of those hydrogens should be. I know that their bond length is 1 angstrom, and I know what the ideal bond geometry should be. So we create the hydrogens, we add the water, and then we run a small energy minimization. And then we're more or less ready to start the simulations.